Good. So, hi everyone. My name is Jacques Renaud, and we are from Laval University in Quebec, Canada. I am here with my colleague Khaled, which is in somewhere in the room, and my colleague Leandro Coelho. And this is a joint work with Vincent Turgeon, which is from the Department of Information Technology of the city of Trois-Rivières, or Three Rivers in English. So I will first present the situation we face, then have a good look at the description. I will start my timer. Okay, look at the data and all the adjustment that we made to be sure that we have a precise simulation, and then how we manage the traffic lights, and we will present some results. In fact, I have very detailed results, but I saw also some global one if I don't have time to pass through the details. So this is a joint work with two partners. The first one is the city of Trois-Rivières, and the second one is a common carrier. It's a heavy duty carrier called Somavrac, which performs all day long back and forth trips on the busiest boulevard of the city. So the objective is to see how we can improve the fluidity on this boulevard and eventually reducing the consumption of this truck. We are lucky because we have complete coverage of the road with remote camera and traffic light control systems, because the city is equipped with those systems. So it will help us to have precise data and eventually to implement the new policy. So clearly we have to model the city traffic, and then how develop some policy to control traffic lights to reduce congestion and eventually decrease fuel congestion. So just to situate our problem, the city of Trois-Rivières is a small city between Quebec and Montreal. So yes, in Canada here, it's still the night. So it's a beautiful city around, it's less than 2,100 people. So it's a beautiful place. And we are very lucky because we have a complete access to the latest origin destination study of the Quebec Ministry of Transport. And this OD study, in fact, covers 18 administrative regions. So this is this complete map here, which is covered by this study. But we will need to focus only on this heavy section here. So the complete networks is around 18,000 segments. And in the first step, we produce a complete 20-hour simulation based on this OD study. And we have to apply 6 other steps to calibrate carefully these data. And I will show you these steps in detail. So remember that in a survey, they survey around 20% of the population. So in a line of the survey, each line is a sample, which is multiplied by a multiplicative factor. So as it is a sample, the trips in the OD are generally aggregated within a 15-minute interval. So if we use these data, we will not have a smooth curves. So in the simulation, we took each trip and we spread them in a 10-minute interval and within a 500-meter buffer zone. And you have 2 curves here. The orange one is the traffic profile of the entire region. And the gray one here is the traffic curve of our main section. So as you can see, both have exactly the same profile. Then we, as I said, we reduce our section to this white polygon here. So we have a lot of trips starting from the 18 region. And in this section, we concentrate only on the trip passing through this area. So we have to intercept each trip. And for doing this, we use the cut routes function to produce a reduced trip file. And now we have 262,000 vehicle trips. And finally, we run the dynamic user assignment procedure one shot to balance these user routes. In the next step, we obtain observation from the city, and the objective is to reproduce the kind of vehicle that are traveling on the city. So we use 7 different types of vehicle as well as their emission class. So we try to be as close as possible as the type of vehicle that are on the road network. In the 4th step, we have access to camera. These are LiDAR technology, so we can count exactly how many vehicles are passing through each of these 24 road segments. We have 88,000 such a vehicle per day. And the objective here is to make sure that our simulation has almost as possible the same number of vehicles on these 24 important road segments. And for doing this, we use the calibrator function of Sumo, which increase a bit the number of trips up to 289,000. And here we are proud to have a very good precision, almost 99%. We are at 99% close to the observation of the city. So for this section of the city, we are very close to the origin destination and to the field observation. In step 5, we model our partner truck because, as I said, this truck performs back and forth trips all day. This truck is equipped with GPS and we have all information about the engine consumption and all other detail. And we use 2 different consumption class to model the truck. When the truck is full, the truck is about 50 tons, and on his back trip, the vehicle is empty. So we use only a 25-ton vehicle. Finally, we implement exact traffic signal phase through the 13 lights on our path. And for doing this, we have access to the programmation sheet. I don't know how we call these documents, but we enter each of these 13 intersections very carefully in order to be sure that we reproduce the way the lights manage the traffic. So this is how we develop our simulation engine. And the next step is to try to connect. For sure, we connected the truck to the lights by using a sensor. and the simulation was run under the 3C environment. If you have any question about the simulation, my colleague Khaled performed all the detail. He is the one who coded the simulation, so feel free to send him an email. He will answer you. So the first strategy is in fact the statu quo. We do nothing. We just run the simulation and take the information. Strategy 1 is an extreme strategy where each sensor is located at 150 meters of the intersection. And as soon as the truck reaches the sensor, the lights automatically switch to green. In strategy 2, we optimize the location of each sensor in function of the speed on the road. So we try to position the sensor in a way that the truck arrives in the middle of the green light phase. And finally, in strategy 3, we try to be more realistic with respect to the control lights. So we have 3 cases. If we reach the sensor and the light is red, we change the other direction to yellow for alpha second and give the truck a green light. So we have a kind of alpha second buffer here. If the light is green, but for less than beta second, we extend the duration such that it will last at least beta second. So the truck will have the time to pass through the intersection. And in the other case, we take no action because we don't want to interfere too much with the synchronization of the lights. So this is the 4 configuration that we will test. And I have the complete detailed results, but I will go right now to the global one. So in the first column, you have the number of trips generated. In the second column, the percentage of trips. So we can see that we are very close to the percentage that we wanted. We have the consumption, the distance traveled, as well as the consumption in liter per 100 kilometers. And in the column new strategies, we have the reduction, how we improve the global consumption in liter for all the traffic. And first of all, what our first objective was to reduce the consumption of our partner without putting too much perturbation on the whole system. But we were a bit surprised that, in fact, we succeed to reduce the consumption for almost all the kind of vehicle. And as you can see, we obtain a very interesting global reduction. So the next step is to understand why. And when talking with the people of the city, it is well known that the boulevard has a very high congestion problems. And actually, we believe that by giving more green lights on the main path, we help to have a better traffic. So in the next step, we will try to identify clearly which car has a very good reduction in order to see if these reductions are effectively in the main path, in the same path of our truck. In short, we believe that as the truck has a free access to all the green lights, the traffic flows with the truck and it helps the global system. This is our hypothesis at this point. So we have complete detail for each strategy. So for sure, when we and maybe some of you can help us to understand these details, but when we change a strategy, sometimes the number of trips move, it change. And we are performing new simulation on that project. And sometime when we change the sensor, we have 2,000-3,000 trips more. So this is a question that we should resolve before going further. So we have here the result of each strategy. And finally, some simulation statistics. And after all these adjustments, we have very few teleports. I think that it's less than 0.2% of teleports in the system. So we believe that it's a good reproduction of the system. And in conclusion, I use the word digital twins. I'm not sure that it's good, but we succeed in performing a precise simulation, and we show that it is possible to reduce the fuel consumption from our partner, and we also found some positive outcomes for the overall traffic, which is a good finding also for the people of the city. So I think that I am right on time. If you have any question, feel free. We'll try to do our best.